for any reason?
I can see your slides now.
Great. Okay. So once again, thank you for the opportunity to speak here. I wanted to tell you a little bit about some of the things that we've been doing in my group. But since this is the very first talk of the conference and also a tutorial, I thought it could also be a great opportunity to mix that with some more pedagogical introduction to some of these topics. So the talk will pretty much have two parts, one which is more related to classical stochastic thermodynamics and one that is more quantum mechanical. So I think that will be kind of a nice, it will fit nicely within the scope of this conference. So let's get started. And just to kind of motivate a little bit the kinds of things that I want to talk about, let's just discuss this idea of thermodynamics and fluctuation. So what I wrote down here is a textbook or Wikipedia level discussion of the first and second laws. So the first law is essentially talking about how the energy balance, so the energy U of a system changes in time, and this can be related to heat flowing to reservoirs and also to power, output power that you might extract from a machine. And then you have the second law of thermodynamics that says that for entropy, you get something a little bit different. So the change in entropy of the system has these kind of two terms here, which you can think about them as kind of flows of entropy. But there's also this very special term, which is called the entropy production rate. And it is, according to the second law of thermodynamics, it is larger or equal to 0. So while energy satisfies a kind of a balance equation, entropy does not. And this is the basis for a lot of thermodynamics. So for example, one of the natural things that one can do is calculate the efficiency of a machine as just the power divided by heat from the hot bath. And by just playing around with some of these equations, just literally moving things, and substitutions, you can write that the efficiency can be written in this very cute and very famous way, where the efficiency is the Carnot efficiency, that's the thing inside parentheses, minus something. And this quantity is actually negative because of the second law, right? And so this simple result shows that, you have to, when you produce entropy, when you have entropy production, efficiency goes down from the Carnot efficiency. And that's one way of stating the second law. Now, in practice, if you're designing a machine yourself, you would want to optimize the power. The speed dot is really what matters. You want to get power out of your machine. So once you fix a given level of power, then you can ask, what's the best efficiency that I can do? And I illustrate this here with this little plot in blue. I'll explain later how we can actually construct this kind of plot. But the basic idea here is that, you just parametrically plot for whatever engine model you have, you plot the power, the efficiency as a function of the power. So for example, if you choose a power, let's say 0.08 around here, you will essentially have a range of efficiencies that you might be able to have. And of course, then for this fixed power, you'll want to optimize your efficiency. Now, the reason why I'm showing this plot is just to note that if you want to have some power out, so if you want to extract power from your machine, you also have to produce entropy. So this is the entropy production, right? And so this is the famous kind of trade-off between efficiency and dissipation. What we care about is the power that we extract. And to do that, we actually need to produce entropy. But by producing entropy, we make our engine less efficient, right? And we have this trade-off. So this is kind of the basic idea of thermodynamics. And this kind of discussion has been present for 200 years almost. It's this kind of very basic idea between being efficient or dissipating a lot of heat. Now, what changes? What is new to our field of research? What is new to stochastic and quantum thermodynamics? Well, what's new is that if your device is now small, then all of a sudden power fluctuations become important, right? And you have this idea that not only you have to think about the average power that you might extract, but you have to think about power fluctuations. So, how stable is that power? And this will be kind of the topic that I want to talk about today, how to define this idea of fluctuations. So you might have seen these concepts before. One very famous scenario in which they appear are these thermodynamic uncertainty relations that appeared 15 years ago. So the thermodynamic uncertainty relations, they are essentially bounds that relate the fluctuations of a thermodynamic current, could be power, could be also heat, divided by the average squared. So J here is the average current, and D is the fluctuations of that current. And essentially, the thermodynamic uncertainty relation states that this has to be essentially lower bounded by something that depends on the entropy production. So this kind of bound has attracted enormous interest. First, because it implies an interesting trade-off between fluctuations and dissipation. Essentially, it says that if your goal is to reduce fluctuations, you have to pump up the dissipation. It's also attracted interest because when you go to quantum processes, this bound can be violated, and this is due to quantum coherences. So there has been a lot of interest in understanding why quantum coherences can violate such a bound, right? And so this has really been a major field of research. But what I want to address here for the first few minutes of this talk is a much more basic question, which is, what is this actually, this current fluctuation, this D? What does it actually mean, right? So sometimes you'll hear people say that this is a current variance, it's the variance of the current, right? It's not exactly the variance of the current. I'll explain in a second. For me personally, maybe because I didn't come from this field, this was very confusing at the beginning. And I've had many discussions with colleagues who are also very confused about this quantity D. What does it actually mean? And how do I think about it? What is the intuition behind D? So here's how we define it. Let's first talk about the definition. So the point is that when you have a stochastic process, this can be quantum or this can be classical, the current itself, right, is a stochastic process that is usually point-like. Every, at random times, you might have random clicks. A current is a sequence of clicks. This could be a click of value, positive or of value negative. This would be, the case, for instance, if you're talking about a particle current or an excitation current. And the current itself is this kind of stochastic process, okay? Now, from something like this, from this kind of structure, you can define the average current. That is fine, right? But you can't really calculate the variance of this current because this is a very singular kind of stochastic process. So if you try to just calculate the variance of this object, it is very ill-behaved. So instead, here's what you do. You first define the charge. Now, given a current I of t, whatever you like, the charge for me is going to always be the integral of that current. So Q is the integral of I, and I is the derivative of Q. Okay, so this is the integrated charge. And now the way that the noise is defined usually, the way that this thing D is defined, is as the rate of change of the variance of the charge. So you see, it is kind of related to the variance of the current, but also it isn't, right? It is definitely different. So some people will call this a scaled variance or a diffusion coefficient or noise. I mean, I would probably call it the noise throughout, but all of these terms are widely used. And so this is how this quantity is properly defined. Yeah. And I find it interesting because, there has been so much drive into studying these TURs, into essentially bounding this D. And we don't really appreciate, at least I don't appreciate, let me put it this way, why does this quantity really matter? How do I think about it? Why do I care about it? And how to, gain some intuition on how it behaves. So let me throw out here a couple of bits of information that might help us a little bit with the intuition. So first of all, there is one interpretation that is very operational, and I thank Mark Mitchinson for pointing this out to me. This is discussed in this tutorial paper that we have here. Suppose you measure the charge, okay, over some fixed interval t, big T, yeah? So you calculate essentially the sample mean of the current. So the charge divided by the duration of the time. And now you want to think about this as an estimator for the actual average current. So you want to look at the error between this quantity, which are using to kind of estimate the average current, and the actual average. And what you can show is that this scales as D over T. So this is a nice interpretation. Essentially, the noise is the thing that is related to your ability to learn the average current. When you try to learn the average current from measurements, your knowledge is going to improve because this goes down as 1/t. So the more you integrate, the more knowledge you get. D is the coefficient in front. I think that's pretty cool. The second possible intuition that you might get is that one can show that D is also the integral of the current two-point correlation function. So instead of looking at the current at time t, you look at the current at 2 times t and t plus tau. You subtract the average squared. So this is what's called the two-time correlation function. And the current is essentially 2 times the integral of this. Now, this result is nice, but also it isn't, just because, at least for me, the two-time correlation function is a very intuitive thing to think about. It's essentially how, the current at a given point in time is correlated statistically to the currents in the past or in the future. So for me, it kind of makes sense to think about current correlation functions. And of course, this correlation will be reflecting timescales in the problem, timescales to the loss of information, and so on. The noise is already the integral of this, and I already find this a lot less intuitive just to think about. Okay? But this is an improvement. Okay, so now to kind of gain a little bit more understanding about these kinds of processes, let me discuss a little bit the formalism that we can use to model and think about noise. So like I said, I'll do this in 2 parts. For now, I'll think about classical master equations, then we'll go on to talk about quantum master equations. So here is the kind of scenario that I'm going to consider. I assume that I have a system that can occupy a discrete set of states and evolves according to a master equation like this, where essentially the dynamics is described by a set of transition rates, W, of L, X, and Y. And the logic here is that this is the rate to observe a transition from Y to X due to Beth L. So L here labels the different reservoirs that might act in your system, right? And they drive these transitions from Y to X. So I'll usually use this kind of symbol to denote a transition from Y to X due to reservoir L. Yeah. And so the master equation has these transition rates and also some escape rates, these gammas, which are just the rates for which the system might jump out of a given state. I'll talk more about this in a second. And just to fix the notation, I will often write this equation in vector notation. I'm using Dirac notation here because I'm silly. There is absolutely no need to use Dirac notation. But I will write this as a vector P. And so this equation can be written as, a bold-faced W times P, where for me, this bold-faced W is a matrix W that has no diagonals minus something in the diagonals. And then the solution is just the matrix exponential of this quantity. Very simple, very direct. However, this equation is all at the ensemble level. What this describes is the dynamics of a probability distribution at the level of the ensemble. It is much more important to think about what is going on at the level of single trajectories. And what's going on is that the system will always be jumping up and down. So a stochastic trajectory might look something like this, right? It's random residence times in different states and then random jumps. And this happens indefinitely, right? The system will just keep doing this indefinitely in time. So to build a stochastic trajectory, we just need 2 rules. To say, for example, you want to simulate this trajectory, we only need 2 rules to do this. Rule number 1, whenever the system is in a state Y, the probability that it will take a time tau for it to jump is given by an exponential distribution with this rate gamma Y. So the residence times in each state are exponentially distributed. Rule number 2, whenever the system jumps, it will choose which state it's going to jump to, and it will jump to state X due to Beth L with probability given by the rate properly normalized. Okay, so the rates give you up to a normalization the probability that when the jump happens, it will go from Y to X. And now with these 2 rules, a stochastic trajectory is fully specified by this list of states, residence times, and Beths. So you say, well, the system starts in x0, it will then jump to x1 after a time t1, and this jump occurred due to Beth L1 and so on. Okay, and here, just to kind of clarify, I'll usually use t to denote absolute times, and I'll use tau to denote differences. So tau is like the duration of a residence, and t is the absolute time. Okay, and so then a stochastic trajectory can be viewed in this way: is essentially a residence time in x0, a jump to x1, a residence time in x1, a jump to x2, and so on and so forth. And by continuing this way, you can build any kind of stochastic trajectory you would like.
Before going to the next slide, perhaps there is a question by Pranay Nayak.
Mm-hmm. Yeah.
Hi, thanks for the opportunity. So I assume that you have this Poissonian jump rates. So is it important that the jumps are rare? It's more likely to stay in the state rather than jump.
Yeah. So the jump probability is assumed to be exponentially distributed, which is sometimes people call it Poissonian, but this is kind of the basic assumption here. And this is crucial for the system to satisfy this kind of master equation. If this was not true, the evolution at the ensemble level would be completely different. And so what this means is that, yeah, if you look at a specific dt, like a small time interval dt, then you're absolutely right. It's always more likely that the system would just stay there instead of jumping. So you have these dynamics, which is essentially, these plateaus for significant times where the system just doesn't move, and then eventually it just jumps abruptly. Yeah.
Thank you.
Yeah. Okay, so let's talk a little bit about interpretations. So the system will eventually reach a steady state, which we call PSS, right? And the steady state can be interpreted as the average amount of time that the system spends in state X. So if you look at a trajectory like this, and you look at the time it spends in each state, this is related to the steady state. From the steady state, we can also build what's called the dynamical activity. And this is the number of jumps per unit time that are observed on average. So P steady state times the rate, so WP, it gives you the average number of jumps from Y to X due to Beth L. Just as a kind of a comment, in addition to the steady state, you can also define what we call the jump steady state, which is essentially the steady state times the rate gamma divided by this dynamical activity. And this represents how often a system will visit each state. So there's this subtle difference, which I took me a while to appreciate, but now I find it quite important, that it's very different to think about how much time a system spends in each state versus how often it visits a given state. These are not the same thing. Okay. Now, where does the thermodynamics come in? This is the important bit. It comes in through what we call linear counting observables. So imagine you have a trajectory like this one in blue here, and suppose that it has a fixed duration that's called t, right? And now we're going to construct a random variable. I'm going to call it nLxy, which is just a counter. It's going to count how many times the transition from y to x due to Beth L has occurred, right? In this interval t. And now from this, we define a linear counting observable to be any linear combination of these counting variables. So we take any linear mixture of these n's with weights nu. So these new Lxy, they're arbitrary weights that you can put in that will define your linear counting observable. And the physics comes in the different choices of nu. So, and this is super interesting and super powerful because now you can ask many interesting and important questions about your process. So for example, if you put nu to be exactly 1 for every possible transition, this is the dynamical activity. Your counting observable is just counting during that duration t, how many jumps happened. On the other hand, if let's say you put nu to be 1 for one specific reservoir, and then 0 for all of the other ones, you're essentially asking the question, how active is that specific reservoir? So, which reservoir is clicking more than the other, and so And you can also then build thermodynamic currents. So for example, if you choose your news to be related to, the inverse temperature of a given reservoir and the energy differences. So this is the thing, which makes sense when the system satisfies detailed balance. Then you can build the entropy production by just multiplying this n by this specific weight. And you can do the same for any other thermodynamic current. You can do the current for the cold bath, the current for the hot bath, and so on and so forth. Okay. So now what do we get from this? Well, we can first think about the stochastic current like we were thinking before. The stochastic current is the rate of change of the counting observable, right? So the counting observable is the stochastic charge and the current is the derivative of that. And so this will be your weight nu divided by dt if a jump occurred in that time t and 0 otherwise. And using this, we can build the average current. We can build the average current because the number of jumps that occur, the number of jumps of this form, y go to x due to BEF L, the number of jumps that occur in the interval dt is just dt times the activity of those jumps. And so the current is going to be just given by this. So this is a very interesting, very powerful way of building thermodynamic currents. You take the steady state, you multiply by your transition matrix, and you weight your transitions by some set of coefficients, nu, L, X, Y. Oops, sorry. We can write this formula for the average current more compactly. So I'm going to define a matrix that I'm going to call W1, which is just the entry-wise product of nu and W. And then we can write this average current as just the sandwich of W1 between the steady state and this special state 1, which is just a vector with all entries equal to 1. Yeah. So this is a compact formula for the current. It's just the sandwich of W1 on the steady state. Yeah. So for those of you who are more familiar with the quantum version, this is this classical analog of the trace, of taking the trace of a density matrix. And now we can do something similar for all other kind of quantities, in particular for the noise. So first of all, we can define the current two-point correlation function, and we can show that this two-point correlation function will have two terms. One term depends on this W2 that is defined exactly like W1 here, but with nu squared instead of nu. And it's a delta correlated term. And then we have another term that is associated to the decay of the correlation function with time. And so this has the form W1 evolution e to the WT W1 trace, yeah? Minus j squared. And the noise is now just the integral of this. And so it will have these two components. Again, you have this first component that is associated to this delta correlated term here. And then we have a term that is associated to this integral over t. And this term, you can write it compactly, if you like, in terms of what's called the Drazen inverse. I will not give any more details about this. If you want to hear more about the Drazen inverse, I recommend having a look at our tutorial. But this is a very compact, very simple, very efficient way of writing down the noise. So if you have any master equation, if you have your W, if you know what current you want to look at, this is a very simple, very easy way to just compute the fluctuations, to compute the noise. And let me give you an example. Suppose you have what we call this three-level maser. It's a system that has 3 levels, and we set up the following rules. The system can go from level, let's call it 0 to 2, because of the interaction with a hot bath. It can go from 2 to 1 due to the emission of or absorption of a photon. And it can go from 1 to 0 by dumping energy to a cold bath. So in this case, there will be, our index L has 3 labels, H, C, and W. And there will be 3 transition matrices, a transition matrix for the hot bath, for the cold bath, and for the photon, the emission and absorption of a photon. The hot and the cold bath, they will essentially be related to the Bose-Einstein distribution of these baths. And the transition of related to the photon is some parameter G that is related to how the atom couples to the photon. And we can now have weight matrices that can calculate for us the current of transitions to the hot bath, cold bath, and also the photon current. So these matrices, they will give us both the average and the fluctuations of, let's say, the number of emitted photons and so on, right? And they will give us precisely the quantities that we started with, the hot heat, the cold heat, and the output power. And so this is, for example, how I built those plots at the very beginning, okay? I solved exactly that model. I got the following formulas for the average quantities. I'll just leave them here for future reference. They can, all of the average quantities can very nicely be written in terms of a current of excitations, let's put it this way, n dot. So you can write hot heat, cold heat, and so on. And the way I make these plots is by just parametrically plotting, let's say, the efficiency versus power by changing some of the parameters. So I just wanted to put this here for completeness. I didn't write down the formula for the noise just because it's very ugly and would take up half of the slide. Very good. So the results that I have shown you so far, they provide us with a very systematic way for calculating the noise in a system described by classical master equations. Are there any questions about that before we move on?
Please raise your hands in case you have a question.
Okay, so let's continue. So I think these results that I just showed you are useful because now you can, construct your favorite model and you can calculate the noise and you can learn, how it behaves as a function of the many parameters of the model and so on. But you see, it's not super easy. Like even this model, right? This is a very simple model. And there are a lot of free parameters. You have coupling strengths, you have frequencies, you have temperatures, and so on. So there's already a lot of free parameters that one can play with, even in this, which is one of the simplest models we can construct. So it is not easy to gain intuition about how the noise should behave. So if I ask you, how does the noise scale with the temperature of the hot bath? Does it go up? Does it go down? It is not always easy to have intuition about that. And this for me has always been a really big issue to just, gain more intuition and how to think about the noise. So to do that, I wanted to share a little bit, a very recent work, actually ultra recent because it appeared on the archive today. That was led by two of my PhD students, Guilherme Fiuza and Abe Hegde, and also counted with the collaboration of Pedro Harunari from Luxembourg. So we're really excited to show this because for me, I think this really opened my mind on how to think about fluctuations and how to interpret the noise in these kinds of open stochastic systems. So the basic idea to kind of motivate it is I wanted to describe this experiment. So this is a very recently published experiment by the group of Simone Gasparinetti in Sweden. And it's one of my favorite experiments in the last 5 years for sure. So what they did here was they considered a on-demand absorption refrigeration. So they have a system with 3 qubits, red, blue, and green. And their goal is to cool down one of their qubits. So they want to cool down, in this case, the cold bath. And the way an absorption refrigerator works is as follows. So you have 3 qubits coupled to 3 baths. And the bath temperatures are such that you have this TW, which stands for a work bath. And it is the hottest of all of the 3 baths. So TW is larger than TH, which is larger than TC. Your goal is to cool this one, is to extract energy from TC. And so the basic idea of an absorption refrigerator is that if the cold system was not here, if it was not present, you would have a flow of heat from TW to TH. That is the natural direction of heat flow. However, things are designed such that the frequency of this qubit does not match the frequency of this one. And so this effectively blocks the flow of heat. However, things are further designed such that there's a triple resonance where omega W plus omega C matches exactly omega H. And this means that you can actually convert 2 excitations, one here and one here, into a single excitation here, right? And so that's the basic idea of an absorption refrigerator, is that you kind of have this machine. So the machine that I drew here is like, TW and TH. And every time there is an excitation in here, in the code bath, this excitation will be sucked off by the machine to allow heat to flow kind of in this direction. And however, this is one of the reasons why I like this paper so much is because it shows us that the operation of these refrigerators, they shouldn't be, thought of as something that just is at steady state. Like steady state doesn't matter too much here. I mean, they really introduced this idea of being on demand in the sense that the way they kind of formulate this, the qubit that they're trying to cool is maybe part of a quantum computer, for example, or something like this. And so it's doing something else. And so whenever you want to cool it, you have to do it on demand. You have to extract heat as fast as possible and as efficiently as possible, right? So questions such as just a steady state current are not really that relevant. The question changes. And what I've learned over this past year is that the most important question is what is the question? Because when you think about these stochastic processes, there are many questions that you can ask. And they're all interesting in their own ways. So for example, how long does it take for this device to cool? If I put an excitation here, how long will it take on average to be sucked off? Or what's the variance of that? And how many ways can this go wrong before it actually goes right? Because it could be that I try to cool it and I fail. And this would be, I could actually heat up this device instead of cooling it. So what's the probability of heating up instead of cooling? And so on. So the questions change. And we've been thinking a lot in our group about what are the right questions to ask. So just to kind of write down how this model would work for concreteness, we could model that system as something with 5 levels, and we can write down some kind of transition matrix. There's also a nice way to convert the quantum model, because that's a fully quantum model, into this classical model. You can do a perturbation theory. This is discussed in this paper here. And so you can write down just a classical master equation, even though the model is originally quantum. And that's pretty cool, because then we can apply all of the ideas that we just discussed. And at least at the regime that they're working, this is a fantastic approximation. Okay. So now this brings us to this idea of stochastic excursions. Okay. So in many physical systems, you have certain states that are kind of special in the sense that they're recurring. They occur over and over again, and they have kind of a special physical significance. For example, in that model, you have this special state, which is the 0, 0, 0, the state where nothing is going on, right? And a stochastic trajectory will essentially mean that the system is jumping up and down between all of these states. And so it's constantly coming back to the state 0, 0, 0, okay? So the basic idea that we're going to try to do is we'll break down a very long stochastic trajectory in terms of individual excursions away from this reference state 0. In reality, we don't even need to have an excursion to be from a single state. What we can think of is getting our state space and dividing it into regions. We have region A. You can think about it maybe as like an inactive region, but that's not necessary. And you have a region B that you can think about it as an active region. We're now going to define an excursion to be the event that starts whenever the system crosses from A to B. And it ends the first time the system returns from B to A, right? In between, the system can do a bunch of stuff in B. So it starts going from A to B, it does a bunch of, whatever transitions in B, and eventually comes back down from B to A. That's what we call a single stochastic excursion, okay? Now, we, of course, initially were thinking about this idea in the context of thermodynamics. But, if you think about it for just a little bit, you realize that this is kind of a much more general idea, right? So here is an example of a university administrator that might be, doing some, admin work. So maybe the person is idle. They could be idle on Instagram or idle on YouTube. These are different types of idle states. And then maybe a new task arrives. So a new random task arrives. This person starts doing something, maybe, booking a colloquium or something. So, composing emails, speaking to faculty, booking seminar rooms and so on. Maybe in between, another test might arrive and so on. But then eventually, the administrator will come back to idle, right? And this concludes the excursion. And so the questions that we're interested in is how to describe counting observables at the level of single excursions. That's really like the original thing that we started thinking about. So instead of asking, say, how long does an excursion take, which is an older question that has already been answered, we want to ask, how do counting observables behave in this single excursion? So for example, how many emails were sent? How many clueless grad students did the administrator have to interact with? How many two-factor authentications did the administrator have to put in to get all this done? Which the answer is clearly infinity. But anyway, that's the basic idea, right? So counting events and counting things that might happen during an excursion. So here's the formalism. We consider a master equation that has a same form that we had before. And we are going to split the transition matrix into blocks. So we have A, B, and you have the matrices that connect A and B. And now we're going to consider an excursion that starts in a specific state XA and ends in a specific state YA. First, we can describe the time that an excursion takes. Like I said, this is something that has been extensively studied in the past. The probability that it takes a certain time t for this excursion can be written in this neat, compact way, where you start from XA, you go to B via this matrix WBA, you evolve in B for a certain amount of time, and then you come back to A via WAB. And then you end up in a state YA. So this is the basic kind of structure for how to describe the time of an excursion. And this quantity C is just a normalization constant. This kind of formalism here, we are assuming that you start in a specific state in A and you end in another specific state, but it is trivial to generalize this to steady state conditions. You just replace XA by the steady state and you replace YA by the state that has all ones like we had before, right? So this gives you access to this first passage times for a single excursion. Very good. Now, the thing that we really want to describe is the statistics of counting observables. So suppose we have R different counting observables. I'll call them Q alpha, where alpha goes from 1 to R. And define now what we call this tilted matrix, which is a matrix that has essentially, whenever you have a transition, X different from Y, we're going to add to the transition matrix a counting field. So we add those little weights that we had before, nu, times a counting field psi alpha. And whenever we have the diagonal elements, we don't change it. And now the first result that we showed is that the probability, so this is the joint probability distribution for all counting observables and for the excursion time as well, can be written as just a Fourier transform of something that makes a lot of sense. So the basic idea is, again, you start in XA, and then you're taken to region B by this matrix here, and the counting fields are picking up anything that you want to count, right? So that's the idea of this tilted matrix, is that as the system evolves, the counting fields will pick up the statistics that you would like. So first you go from A to B, then you evolve in B for some time, and then you fall back from B to A. And then you have to just do the Fourier transform of this, right? And so this is the general formula for the joint probability of counting observables and time in a single excursion. It looks a little bit ugly, but it's actually not too bad to evaluate. So if you have a look at our paper, you'll see we have developed several techniques for being more practical and for evaluating this quantity in practice. So some results that follows from this idea. First, we found that stochastic excursions satisfy fluctuation theorems. So the probability of having an excursion from X to Y and producing some entropy sigma, or from Y to X and producing minus sigma, is related to each of the sigma times this correction due to some those normalization constants. This result, in fairness, it is not at all original. This is just the Seifert's trajectory level fluctuation theorem written for a specific excursion. Okay, but it is an interesting it is interesting to see how it naturally emerges. Once we have this probability distribution, the other nice thing that we can do is we can build all kinds of statistical moments in a very efficient way. So you can build the average of an excursion, the variance, and much more interestingly, you can look at correlations between counting observables and even correlations between excursion times and counting observables. So this one in particular is quite nice because it allows you to do inference. Okay, so suppose your region B is kind of not accessible, right? You can tell that the system went from A to B, it spent some time in B, and you can tell that it came back to A, but you don't really know exactly what happened in B. So if you know the time of an excursion, right, can you make inferences about what was, for example, the entropy production, right? What is the best guess you can make, the optimal predictor you can make about the entropy production given some excursion time, for example? So this is the kind of question that you can ask with this kind of statistics. Finally, we have a very interesting, and this for me was something that was personally very important because it goes back to the very beginning of this talk about the intuition behind the noise. We have a connection between the stochastic excursions and steady state noise. So to establish that connection, we have to assume that region A has only one state. I'm going to call it X. So it's like in this model here, where you have only one state in region A. Now, I need a couple of definitions. I will define calligraphic N as the number of excursions during a very long time interval T. So the basic idea is that you just look for you just look at a trajectory like this for a very long time, and every time that the system completes an excursion, you count +1, and this builds your N of T. During each excursion, I'll define Qn as the value of a specific counting observable that I'm interested in during that excursion. And I will also define tau xn as the residence time that the system spends between two excursions. Because the way that the timing works for excursions is that you have an excursion time for the system to bounce around here, and then you have some residence time that the system spends here before the other excursion starts. And we're going to call this the cycle time. So the cycle time is the time of an excursion plus the residence time. And these two variables are statistically independent, which is great. Then we can connect the counting observable that we usually use in full counting statistics with the counting observables of a single excursion through this formula. Essentially, the counting observable over the entire interval 0 to t is just the sum of the counting observable at each excursion up until the number of excursions that happened. And there's also this additional constraint that the total cycle time has to be equal to t. Yeah. Now, what is really special about this is that because we assume region A only has a single state, this is a renewal process. Renewal process means that the counting observables at each excursion are statistically independent of each other. So we're summing statistically independent random variables, provided they have this special constraint here all the time. And now here are the main results. So let us define the average cycle time to be the average time of an excursion and the average time that the system spends in X. And let's define the variance of the cycle time in exactly the same